subset we have. So for the set G, we are taking H as the subset of that one. Okay. So H is the subset of G. We call that H as a subgroup of G if H is closed for the composition defined in G. Okay. That means whatever the subset H is there, it has to satisfy the property of the closure property we have now. So that if it satisfies that closure property, with the help of that, if A belongs to H, B belongs to H, implies AB belongs to H, then we'll say that H is a subgroup of the set G. Okay. So that is the definition of subgroup. So you have, if you see in your textbook, you have many definitions. That is 3 to 4 definitions are there for the subgroup. So these definitions, depending on the given theorem or depending on the given problem. So solving of different theorems depends on different definition of subgroups. So almost three are there. This is one. That is A belongs to H, B belongs to H, AB belongs to H. One is another one is A belongs to H, B belongs to H, implies AB inverse belongs to H. Okay. So in another one is A minus B belongs to H. So these, whatever the definitions of subgroups are there, these depend on the given composition or given operations. If it is a plus operation, you will have one definition. If you have the multiplication, you have another definition. And if it is a finite group, then you have another definition for the subgroup. So depending on the, you will have different definitions here. So first point is this one. And second one is H itself is a group. Okay. H itself is a group for the composition induced by that of G. Okay. So by the whatever the definition we have for the subgroup is that H itself will become a group for the composition induced by that of G. Okay. So first G we know that G, if it is a group, then whatever the H is there, H automatically it will become the group by itself by satisfying all the properties of the group here. Okay. So that is whatever the second point is there, that you can elaborate it as if G comma plus is a group and H is subset or equals to G. Okay. G comma plus, that is a set G with respect to with operation addition. If it is a group and H is subset or equals to G, then H comma plus, that is set H with operation plus should also be a group. Should also be a group. Okay, that means whenever G comma plus is a group, so whatever the subset we are taking H as a subset, which is subset or equals to G, so that H comma plus with respect, we know this is the algebraic structure, no? So this algebraic structure should also be group. Okay, then only we will say that H is a subgroup. Okay. So in this we have, after the subgroup, we have proper subgroup and also improper subgroups. Okay. So on this also you will have some theorems. So proper and improper, or we call improper as trivial. Okay. Trivial subgroup. So what groups are called as a proper subgroup and what groups are called as improper subgroups. Okay. So every group G of order greater than 1 has at least 2 subgroups. Okay. Every group G, we know that order, I have told, the number of elements present in the set is called as the order of the group. Okay. So whenever you have set G has order greater than 1, means more than 1 if it has the elements, then 2 at least subgroups will be there. That will be, one will be G, means the group, whatever the set is there, the set itself, and also another one is the identity element. That means whenever a group is having the subgroups as G and itself, we call it as a that is identity element. It is the improper subgroup. Improper subgroup means whatever the set is there, set itself and also identity element. Other than these two, that is group itself and also identity element, whatever the other elements are there or other groups are there, subgroups other than G and E are known as proper subgroups. This is the definition of improper and proper. Improper means only two. Proper means other than those, whatever the subgroups are there, those are called as proper subgroups. Okay. Every group G of order greater than 1 has at least two subgroups. At least two subgroups. Okay, which are, there is G itself, and second one is E. E is the identity element. That is the group of the identity. Identity element means only one identity, singleton we have now. So E, that is the group of identity LR. So these two are called as improper subgroups. So identity element satisfies all the properties of. Why we'll take this as a one subgroup? Because identity element satisfies all the properties of group. All the properties of group. So that's why we are taking here E as one of the subgroup of the group G here. Okay. So the above two subgroups are known as improper. The above two subgroups are known as improper or trivial subgroups. Okay. So G itself, the group, whatever the G group is there, the group itself and also identity element, both are known as the improper subgroups. So the subgroups other than these two are known as proper subgroups. Okay. So proper subgroup is subgroups other than G and E. G and E are known as proper subgroups. Okay. Or just proper subgroup. So this is the definition of proper subgroup and also improper subgroup and also what is subgroup. So with respect to of what operation we have, with respect to of the same operation, it has to satisfy all the properties. Okay. Then only we call the H as a subgroup of G. So it depends on the operation here. So next we have one note, that is if any subset of the group G is a group for any operation other than the composition of G, then it is not called a subgroup of G. Okay. So to become a subgroup of the given set, it should compulsory, just now I have told no, it should compulsory satisfy all the properties with respect to of the given operation only. That means if it is plus operation, then only it should satisfy all the properties with the help of plus operation. Then only H is called as a subgroup of G. Okay. So that is given in the this note. Okay. Next, if subgroup examples are there, that is Z comma plus is a subgroup of Q comma plus. And Q comma plus means with respect to of operation addition. Q comma plus is a subgroup of R comma plus. The set E of even integers is a proper set subgroup of additive group. So these you can see here, just I am writing as a note here. That is Z comma plus is a subgroup of Q comma plus. And next one is Q comma plus is a subgroup of R comma plus. That is the real numbers with respect to of addition. Okay. So you have examples here. That is next we have these are the additive groups. That is with respect to of addition we have seen. Next are the multiplicative groups. That means with respect to of multiplication, which set of numbers, that is either natural numbers or integers or rational numbers or irrational numbers or real numbers or complex numbers, which will become the subgroups. Okay. So if it is a multiplicative groups, so with respect to of multiplication, Q plus comma, that is operation is into, is a subgroup of R plus comma into, that is positive real numbers, positive rational numbers. And the second one more, this is the important one. Okay, that is 1 comma minus 1 set and 1 comma omega square and 1 comma minus 1 comma iota comma minus iota are subgroups of that is C naught comma into. C naught means here non-zero complex numbers. Okay. C naught comma X, the group of non-zero complex numbers. The group of non-zero complex numbers. Just if you remember this, it's enough. So what are the examples of subgroups and also what are the examples of with respect to, that is a subgroups with respect to of addition and with respect to of multiplication. So I have told no, two different definitions are there, 2 to 3 different definitions for the subgroup are there. So that you can see in the even in the textbook, what are those different definitions. Okay. So one more is, that is a necessary and sufficient condition for a non-empty subset H of a group G to be a subgroup is that A belongs to H, B belongs to H implies AB inverse belongs to H, where B inverse is the inverse of B in G. That is G comma dot. Dot in the sense is here multiplication we are taking. Okay, this is one more definition for subgroup. Okay, necessary and sufficient condition. A necessary so this you have in the page number 49, page number you have. That is elementary properties of subgroups. There we have that a necessary and sufficient condition. Necessary and sufficient condition. Condition for a non-empty subset. Okay, a non-empty subset H of a group G to be a subgroup, is that A belongs to H, B belongs to H, implies AB inverse belongs to H. What is this B inverse? B inverse is inverse of B, where B inverse is inverse of B in G. That is in set G. Okay. This is one of the definition of subgroups. So starting we have seen one definition. A belongs to H, B belongs to H implies AB belongs to H. That is one definition. This is another definition of the subgroup. Okay. So on this also you have the theorems are there. On this, whatever the definition of subgroup is there, that you can see in the textbook. And one more is theorem 3.3.1. This is also very important theorem. That is, let G comma dot be a group and H be a subset of G. Then H is a subgroup of G if and only if the following are true. The first condition is H is non-empty. That means it should have compulsory some elements. Second one is A comma B belongs to H implies A dot B belongs to H. That is, it is satisfying the closure property. Okay, third one is if A belongs to H implies A inverse belongs to H, where A inverse is the inverse of A in H. Okay. Whatever these concept is there, this is useful in solving some of the theorems. So in doing the proof for the theorems, we will use these all concepts. So up till now, we have seen two definitions of subgroup. Now third one is, if G is a group under the composition of addition, if G is a group under composition of addition. Okay, here specially mentioned that it is the operation is addition. Okay, addition. The statement of the above would be the statement of above theorem would be A belongs to H, B belongs to H implies A minus B belongs to H. Okay. This is one more statement for a subgroup we have. Okay. If G is a group under the composition of addition, the statement of the above theorem would be A belongs to H, B belongs to H implies A minus B belongs to H. So another one is whatever the first definition we have seen, no? The same definition, but it is mentioned that it is a finite subset of G. Okay. First definition, it is not particularly not mentioned that it is a finite subset or infinite subset. Okay. But whenever it is mentioned, you can take one more definition. Let G comma dot be a group and H be a non-empty finite. Okay, especially it is mentioned as finite subset of G. Okay. Then H is a H is a subgroup of G if and only if, okay, you know the symbol, this is a symbol for if and only if A comma B belongs to H implies A dot B belongs to H. Okay, this is one more definition for the subgroup. When the given set is a finite set. Okay, So that is, let G comma dot be a group and H be a non-empty finite subset of G. So H is a non-empty finite subset of G. Then H is called as a subgroup of G if and only if A comma B belongs to H, implies A dot B belongs to H. Okay. So these are the definitions of the subgroups. So next we have that one theorem is there. It is the important one. Almost it will be asked for 5 marks question or 10 marks question. That is the intersection of any two subgroups of a group G is again a subgroup of G. Okay. The intersection of any two subgroups. Intersection we know. If you take one subgroup as H and another subgroup as K, these two are the subsets of G, set G. Then if you take the intersection of that one, that means H intersection K. Here we are taking two subsets now. So H intersection K is also a subgroup of G. So whatever the resultant you are getting as the intersection, that is also subgroup of G. That is the intersection property of subgroup. So this theorem is very important. It is regularly asked. So next theorem is the intersection of any two subgroups. Okay. The intersection of any two subgroups of group G is again a subgroup of G. Okay. So you can choose any two subgroups here, H and K as, you can take H and K or H1, H2, K1, K2 like that, anything you can take. Okay. Those two subgroups such that those intersection is also a subgroup of G here. So here we are taking two subgroups as H and K. So proof is that let H comma K be two subgroups of G of group G. Okay. Then just now I told that what is the improper subgroup is G itself and also identity element. So for solving this theorem, we'll take the identity element. Why? Because identity element is a subgroup of group G. It is satisfying all the properties of group. Okay. So then E belongs to H and E belongs to K. Okay. E belongs to H and E belongs to K, and hence E belongs to H intersection K. Okay, E is the identity element. It is belonging to the subset of the H and also subset K. So therefore, this intersection also belongs to the identity element. Okay. Therefore, H intersection K is a non-empty subset of G. Okay, Non-empty subset of G. Non-empty in the sense it has some elements. Okay. So after that, now A comma B belongs to, now A comma B belongs to H intersection K implies A comma belongs to H and A comma B belongs to K. Okay. So whenever two elements are present in the intersection, so automatically those elements will present in H and also those elements will present in K. Intersection in the sense what? It is a common elements in both the sets. So whenever A comma B are the two elements, when they are present in the intersection, automatically they will present in the set itself also. So therefore A comma B belongs to H and also A comma B belongs to K, implies whenever these, by the definition of subgroup, A comma B belongs to H and also A comma B belongs to K, means we can write it as AB inverse belongs to H and AB inverse belongs to K, no? By the definition of subgroup. Okay. So A comma B belongs to H means AB inverse belongs to H. A comma B belongs to K means A comma B inverse belongs to K. It is by the definition of subgroups. Since H comma K are subgroups, we can take the theorem. It is 3.3.2. Depending on that theorem, we can write this one. Okay. So whenever AB inverse belongs to H and also AB inverse belongs to K, we can write it as AB inverse belongs to H intersection K. Okay. So like this, we can prove this theorem. The intersection of any two subgroups of a group G is again a subgroup of G. So the intersection of those two groups is again a subgroup. It is satisfying the definition of subgroup. So by theorem, we have now 3.3.2. H intersection K is subgroup of G. Okay. So like this, intersection of any two subgroups is again a subgroup. You have to prove this. One note is there for this theorem, that is not only the intersection of only two sets here. It is this, whatever theorem is there, this theorem is applicable for family of subsets. Okay. That is family of subgroups, means more than 2, 3, whatever the subgroups are there, further also this property is satisfied. Okay. So this theorem can be extended to, you can write like this. This theorem can be extended to family of, to any arbitrary arbitrary in the sense now any number of, okay, arbitrary intersection of groups, subgroups. That is the intersection of any family of subgroups of a group is a subgroup. Any family of subgroups of a group is a subgroup. Okay. So you can represent this one like this. If H1 comma H2 comma H3 so on until we are taking Hn, n times of the, so n number of subgroups here. N number of subgroups, if you are taking, be a finite family of subgroups of G, then H1 intersection H2 intersection H3 up till intersection HN is also a subgroup of G. Is also a subgroup of G. Subgroup of G. So like this, we can do the proof for this theorem. So this theorem is even applicable for finite family of subgroups also. Okay. If you take n number of subgroups here, then their intersection is also a subgroup of G. Okay. So this, whatever the concept is there, this is applicable for the intersection of the any two subgroups. Similarly, if you see for the union of that one, so union of subgroups means, so it is not necessary to become the intersection of the two subgroups again a subgroup. Means it is not important that, means it is not compulsory, or it may or may not. So in some cases it will become the union also will become the subgroup. In some cases the union will not become, it depends on the operations also, that is plus operation or multiplication. It may or may not become the subgroup. Okay, so you can say this theorem in page number 52 you have, that is, let H and K be subgroups of a group G, then the union H union K is a subgroup of G if and only if either H is subset or equals to K, or K is subset or equals to H. So if this condition is satisfied, then H union K is subgroup of G. So even if you see in check your progress, fourth one, show that the union of two subgroups of a group G is not necessarily a subgroup by giving an example of two subgroups H and K of group G, such that H union K is not a subgroup of G. Okay. So you can show that one, that H union K is not a subgroup of G. So 3.3.6 theorem is very important. Is the 10 marks question you will get. And even 3.3.7. This is also very important. That is, let H and K be subgroups of a group G and define HK. So here whatever HK is there, it is defined as AB such that A belongs to H and B belongs to H. Okay. Then prove that HK is a subgroup of G if and only if HK is equals to KH. This is one more important one. So these two are the 10 marks question you will get in the, that is the 9B question. So these two are the concepts of subgroups. These two theorems are important. Third one, this is also important theorem. Three theorems are important. From this one you will get for the 5 marks question. Two questions, any one you will get for the 10 marks question. So for the union you have, just now I have told now, necessary. It is not necessarily that union of two subgroups may or may not become. If they may or may not become the subgroup. So you have the theorem one. So what are the conditions for that one? Next one is the union of two subgroups is not necessarily a subgroup. So you can tell that one with respect to one example here. So the union of two subgroups is not necessarily a subgroup. Okay. So this you can show with the help of one example we have. That is the group we are taking, one group G. that is the group. So we are taking the group G as Z comma plus, that is integers we are taking with respect to of operation plus, has two subgroups, So one subgroup is H is defined as 2n such that n belongs to Z, okay, and K is equals to 3n such that n belongs to Z, okay. So H is defined as 2 into n. N you can take as a integers, positive or negative integers, anything. K is equals to 3n. Okay. So H union K. So the combination of these two is that. Okay. So if you multiply with n equals to 0, n equals to 1, n equals to 2, n equals to 3, n equals to 4. So up till 3 if you are taking, then if you take even positive terms and also negative terms. So when the n equals to minus 3, you will get here minus 6. Next minus 4, 2 to the minus 4, no. Next minus 3, minus 2, 0, 2, 3, 4, 6, so on. Okay. This is the H union K. So if you want, you can write here multiples. So H equals to n equals to 0, 0. Next 2 you will get. Next 4, next 6, 8, like that, so on. Here also, if you put n equals to 0, what are the positive terms and what are the negative terms? So H union K, combination of these two, you will get this as the set. Okay. Is not a subgroup of G. Okay. Is not a subgroup of J because this is not closed. Because this is not closed for operation plus. So whatever this H union K is there, it is not closed for operation addition. That means whenever you do H union K, whatever the resultant you are getting, these are not satisfying the closure property. Okay. You can take any one example here from the given two sets only. That is example 2 belongs to H union K. 2 is there, no? H union K, okay? 2 belongs to H union K. 3 belongs to H union K. 3 also belongs to H union K. Then with respect of addition closure properties, there is what? A plus B should also belongs to the H union K. So A plus B means 2 plus 3. 2 plus 3 is what? 2 plus 3 equals to 5. Does this belongs to H union K? It does not belongs to H union K. Therefore, 5 does not belongs to H union K. So by this we can say that the union may not necessarily be a subgroup. Okay. Does not belongs to H union K, which shows that H union K is not closed for addition. So closed property is not satisfied means no need of seeing the other properties. Okay. So if one property is not satisfied means it will not become group. Automatically it will not become the subgroup. Okay. So these are the important theorems. In subgroups we have topic. Unit 3 is about subgroups and also cyclic subgroup. So if we go to the next concept, it is the cyclic subgroup we have. Cyclic subgroup is definition you have in your textbook. A group G is called a cyclic group if there exists an element A in G such that G is equals to, this is called as a generator of G. G is equals to, that is generator of A, that is G is equals to A to the power of N such that N belongs to Z. Here N is the integers we have. Cyclic group definition is nothing but a group will be there. Group is a G. In that, if you take any one element, that element should generate the elements. Okay, that element should generate the elements which are present in group G. Okay, so then only we call that group G as a cyclic group. Okay, this is the definition of the cyclic group. So you can see, understand this concept we have with the help of any example. Okay. A group G is a cyclic group. So cyclic group definition is that if there is a group G is a cyclic group, if there exists an element A, so that should also belongs to G only. Okay, such that G generates the elements of, so that G generates the elements of G. Okay, so A is called as the generator of G. Okay, that is another one we can represent here. G is equals to A to the power of n such that n belongs to Z. Okay, that is every element of G has, every element of G can be expressed as some integral power of A. Okay, so each and every element of the given set in J, if it can be expressed as some integral power of A, then we call that G as a cyclic group. Okay, here A is called the generator of G. Whatever the small a is there, it is called as a generator of G. A is called the generator of generator. In the self itself it is there. It generates some elements. Okay, G. So you can take here G is equals to, even like this also. This is 1, A minus 3, A minus 2, A minus 1, A0, A1, A2, A3, so on like this. Okay, it generates the elements for multiplication. So whenever the operation is multiplication, we will get the elements like this. Okay. If the operation is addition, okay. If the operation is addition, then G is equals to NA such that N belongs to Z. Okay. It has written as like this product. That is example you can take. G is equals to generator of A such that 3A, 2A, A, minus 1, minus, 0, A, 2A, 3A, so on. Okay. So whenever it is addition, you will have the elements like this. Whenever it is a multiplication, you will have the elements like this. You will write as a integral powers. Here you will write as a multiples. In addition, we'll write as a multiples. In multiplication, we'll write them as the integral powers. Okay. You can take here example 1. That is, if set G is equals to 1 comma minus 1 comma iota comma minus iota, then if we'll take any one element, what is the definition? If G, a group G is a cyclic group, if there exists an element from this, if you take any one element such that if you'll do the power of that one, integral power of that one, so then you have to get the all the elements present in the G. If like that you will get, then G is called as a cyclic group. Here if you take one element here, if you take one, what will happen? 1 in the sense 1 square is 1, 1 cube is 1 only, 1 to the power of 4. So any integral power, if you take only single element, you will get. If you take even minus 1 also, minus 1 means minus 1 square is equals to 1, minus 1 cube is equals to minus 1. So only two elements you will get, that is 1 and minus 1. But we need here 4 elements. Okay. So next if you take I. So I is the generator of this one. How you can prove this one means I square. First I we have no, I to the power of 1 is equals to I. Okay. Next I square is equals to minus 1. Okay. I cube is equals to, I square is minus 1 into I means you will get as minus I. Next I to the power of 4 means minus 1 no, I cube into I. Into I means I square is minus 1, already minus is there. Therefore, you will get it as 1. So, okay, you are getting all the elements. 1 you got, minus 1 you got, I you got, minus 1 you got. So, 1 minus 1, I minus 1. So, I is called as a generator of G. Why? Because it is generating all the elements of G. Even minus I also you can do. Minus I to the power of 1 means you will get minus I whole square. If you do the square of that one means, so first I, you have minus symbol, I square is minus 1. I minus into minus 1 you will get. Okay, that is plus 1 you will get. Next to minus I whole cube. So you can see that one, it also does not generate all the 4 elements. So only I is the generator of G. Like this you have to see which element is generating all the elements of group G, that is called as a generator of G, and that group G is called as a cyclic group. Okay. So if you see with the help of addition, this is we have done with respect to of multiplication. If you do with just now we have seen the definition for addition, no? You will have the multiple. That is we have to find the multiples of that one. Or else one more method will be there, that is whenever it is given plus, you have to do the addition of that number that many times. Okay, we'll see one example. Find all the generator of the cyclic group. Find all the generators of the cyclic group. So here group is given G is equals to 0, 1, 2, 0, 1, 2, 3, 4, 5. And here it is the addition modulo 6 we have. Okay. So this is question, in the question it is given that G is equals to, elements are 0, 1, 2, 3, 4, 5. And you have here the operation is addition modulo 6. Okay. So we'll find the solution for this one. So here if you see order of G. Order of G is number of elements present in this group. So 1, 2, 3, 4, 5, 6. So here the order of G is 6. Okay. So whenever it is a multiplication means we have done the integral power of that one. So whenever you are doing the addition, so for which elements you will get the order of G as 6, those elements are called as a generator of that group. Okay. So for addition, you have to check like this. And even same, whatever the elements are present in group G, same elements you will get for that element also. That is the main important thing you can identify. Okay. So if we'll take first 0 is there. If you'll do 0 only one times, that is 1 of 0. That is one time you are doing 0 means 0 is it. So 0 plus 0 is also 0. No? So any number of times if you add that element, you will get the same as 0 only. Okay. So this order of implies order of 0 is 1. Okay. Order of 0 is 1. Next, if you see 1 of 1, that is 1 times of 1. So it is equals to only one time you are doing. So one time if you do, you will get 1. 1 of 2 means you are adding 1 2 times. So you will get it as 2. 1 of 3 means 1 plus 1 plus 3. You will get 3. 1 of 4 means you will get 1 plus 1 plus 1 plus 4. You will get 4. Okay. Next, just 2 1 times, 3 1 times, 4 1 times, 5 1 times means 1 plus 1 plus 1 plus 1 plus 1, 3 to 5. It is equals to 5. Okay. So we got all the elements present in genome. That is first we got 1, next we got 0, next we got 2, next 3, next 4, next 5. So first element is 1 of 0 means you will get 0. So that element is 0 you are getting. Okay. So we got 1, 2, 3, 4, 5. We need third element, that is 0 we didn't got. So for that one, 6 of 1 is equals to 6 of 1 is equals to 1 plus 1 plus 1 plus 1 plus 1, 2, 3, 4, 5, 6. Okay, 6 times. So 6 times means you will get the resultant as 6. But we have additional modulo 6, no? So whenever it is additional modulo 6 means you will get the value as 0. So for 1, we got 0, 1, 2, 3, 4, 5 which are present in G. So this is the generator of G here. Okay. So implies order of 1 is equals to 6. Okay. So order of 1 is 6 here. Next, if you take 1 of 2. Okay, that means 1 time of 2 is equals to 2 you will get. Okay. Next, 2 times of 2. 2 times of 2 means 2 plus 2 is equals to 4. Next, 2 times of 3. Sorry, 3 times of 2. 3 times of 2. That is 3 plus 3 plus 3 means 3, 3, 6, 6, 9. 6 is 0, so you will get 3 here. This is 2, 2, no. Okay. This is 2, 2, 2. So 6 means it is 0. Next, 4 times of 2. 4 times of 2 means 2 plus 2 plus 2 plus 2. Okay, 2 to the 4, 4 to the 8, 8. Sorry. 2 plus 2, 4, 4, 4 means 8. 6 is 0, no? So you will get here 2. Okay. Then 5 times of 2. 5 times of 2 is 2 plus 2 plus 2 plus 2 plus 2. So 10 you will get. Okay. 10 means 6 is 0. So you will get it as 4. Okay. Next, 6 times of 2. 6 times of 2 means 2 plus 2 plus 2 plus 2 plus 2 plus 2. Means 6 2s are 12. 12 means 0, no? So 2 2 4 5 6 7 8 9 10 11 12. So why? Because plus 6 is there, no? Okay. Addition modulo 6 is there. So addition modulo 6 means you will get for that is addition modulo 6 means this you will get it as 0. Okay. So what elements you are getting for 2? 2 you are getting 4, 2, 4. So you are getting the repeated one. So you are not getting all the elements in G. So the order of this one is only 3 elements are there, no? They are only repeating. So 2, 4, 0. So only these 3 elements are repeating. So order of 2 is 3. Okay. So next, if you see 3, 1 of 3 is 1. 1 of 3 is 3. Okay. Next, 2 of 3 is 2 of 3. 3 plus 3. 3 plus 3, 6 means 0. 3 of 3 means 3 plus 3 plus 3. So what you will get? 3 plus 3, 6. 6 plus 3, 9. 9 means you will get 3. So only these elements will be going on repeating. So only 3, 0, 3, 0 elements will be repeating. So order of this one is order of 3 is 2. Okay. Order of 3 is 2. Next, if you see fourth, there is a 4. For 4, if you see 1 of 4 is 4. 2 of 4 is 4 plus 4 is equals to 8. 8 means you will get 2. Okay. Next, 3 of 4. 4 plus 4 plus 4. So 4, 4, 8. 8, 12 means 0 you get. So 4 of 4 is 4 plus 4 plus 4 plus 4. So 4 4s are 16. 16 means 12, 0, 4 you will get. So again 4 is repeating. That means only 4, 2, 0. So you can tell that implies order of 4 is 3. Next what we left? 5 is there. So 1 of 5 is 5. 2 of 5 is 5 plus 5 is equals to 10. 10 means 6 is 0. 4 you will get. Next 3 of 5. 3 of 5 means 5 plus 5 plus 5. 15. So 12 is 0. You will get 3. Next 4 of 5. 4 of 5 means 5 plus 5 plus 5 plus 5. So 5 4s are 20. 20 means 6 to 6 3s are 18, no? So you will get 2. Next 5 of 5. That is 5 plus 5 plus 5 plus 5 plus 5. So 5 5s are, you will get 25. 25 means 6 4s are 24. So 1 you will get. Next 6 of 5. 6 of 5 is 6. Sorry. 5 plus 5 plus 5 plus 5 plus 5 plus 5. 3 3 5. 6 5 are 30. So 0. So you got all the elements 0, 1, 2, 3, 4, 5. So these all the elements are present in G. So therefore the generators are here. For what we got here, order is plus order of 5 is 6. So this is one generator. 5 is one generator. And here where is one? This is one generator. Okay. So the generators of G are 1 and 5. 1 comma 5 are the generators of G. So like this, if it is addition, like this we have to do. If multiplication is there means square you have to do. Okay. So like that you have to find the generators of the cyclic group. So observing the orders of all the elements of G, we find order of 1 is equals to order of 5 is equals to 6 equals to order of G. Therefore, G is equals to 1, 5. That is 1 and 5 are the two generators of G. So you can write here. Observing the order of all the elements of G, we find order of 1 is equals to order of 5 is equals to order of 6 equals to order of G. Okay. Therefore, G is equals to generator 1 equals to 5. Okay. 1 and 5. That is 1 and 5 are generators of G. Are two generators of G. Are the two generators of G. Similarly, you can find with the help of even multiplication also. Multiplication is you have to do the integral power, that is square you have to do. Okay. So just to understand the concept of a generator, I have told this problem. This problem is not there in your textbook. Just to understand the concept of what is a cyclic group. So you have in check your progress, it is there 1, -1 is the group G under the multiplication a cyclic group. You can see that one in the textbook. Okay. So in third unit 3.4.5, 3.4.6, these two theorems are very important. These will be asked for the 5 marks question and also 10 marks questions. Okay. Every cyclic group is an abelian, but the converse need not be true. This is the very regularly asked question. Next one is the 3.4.6 we have. Okay, these two are very important, and even 3.4.8 also theorem. Okay. So one more theorem you have in page number 60. That is 3.4.9. Every subgroup of a cyclic group is cyclic. This is also very important. This is regularly asked question. Okay. So with the help of whatever the concepts we have learned, through that you can do the proof of this theorem. 3.4.9, 3.4.11. These are the important questions. And one more is 3.4.13. Example, you have find all subgroups of Z24. This is sometimes asked for 5 marks question. Okay. So by this we are completing the block 1. So tomorrow we'll start the block 2, that is groups 2 you will start. Okay, tomorrow we'll see the class.